Welcome to lesson number 3 of transformations. We're going to look at reflections, part 1. Okay, so we're going to be doing the same thing we did last class, where we have a graph of f of x, and but this time we're going to have y is equal to negative f of x. This is going to result in a reflection either across the x or y axis, and we're going to be looking at invariant points. Remember when we looked at reciprocal functions, invariant points are points on the graph that are going to remain the same. So if we had this graph of f of x and the graph of y equals negative f of x, there's going to be a point or 2 points for these functions where the coordinates are not going to change at all. So if I look at the graph of y equals f of x, and that is equal to x squared minus 10x plus 25, we want to write the equation which represents y is equal to negative f of x. Okay, so now since f of x is equal to x squared minus 10x plus 25, if I want to represent this as y equals negative f of x, this is going to be negative f of x, which is x squared minus 10x plus 25. And this is equal to y, if I distribute that negative sign inside my function, negative x squared plus 10x minus 25. Now the next thing we need to do is use the graphing calculator to sketch y is equal to negative f of x, and then we want to show what that looks like on the grid provided here. Alright, so let's do just that. I'm going to have negative x squared plus 10x minus 25. And graph. So it looks like it's exactly like this graph. It's got where this graph had a minimum point at 5 and 0, this graph looks like it has a maximum point at 5 and 0. Alright, so let's basically draw the mirror image of this graph here, and there we go. That's what's going on with negative f of x. And if you look at this, what it looks like is, if you're out looking at a mountain or something on a pristine day at a nice lake, you'll see a mirror image of that mountain represented inside the lake or on the surface of the lake. And it's the same thing going on here. We have a reflection across the horizon across the x-axis. So remember how we talked about invariant points? Those are points on the graph which are not going to change after the transformation. There's only one point that doesn't change, and that is this point right here. It was at 5 and 0, and it's still at 5 and 0 after this reflection. So if we state that point, we have a point at 5 and 0. So if we have a function y equals f of x, and we perform a reflection on that function y equals negative f of x, and this is the parameter that we're setting on that function, that's going to result in a reflection across the x-axis. So let's look at another example. Part 2 here. The graph of f of x is equal to x cubed minus 8. Write an equation which represents y equals negative f of x. So we're going to do the exact same thing we did up top. Negative f of x is equal to x cubed minus 8, and we're going to distribute that negative sign into our brackets, into the function, and we're going to have negative x cubed, negative, and times negative is going to give us positive 8. And again, we need to graph this function. And so this time I'm going to graph both functions. I'll graph the original, and I will graph the new function, which is negative x plus 8. And so right away you'll see our original function that's graphed, and we have an exact mirror image across the x-axis that is formed. Alright, so we also want to state the invariant points on the graph, and in this case, again, there's only, if we look at at this graph, there's only one point that didn't change, and that was the one at, looks like 2 and 0 there. But we do need to graph this, and so this is at negative 5, 6, 7, 8, and we're going to be at negative, or at positive 8 here. And so this graph is going to look something like this. And so our variant point is going to be right here at 2 and 0. If we say the coordinates of our invariant point, 2 and 0, that's the point, remember, that does not change. And then we're going to be asked the question, how does the graph of y equals negative f of x compare with the graph of y equals f of x? Well, it's a reflection. It is a reflection in the x-axis. Okay, so let's look at this last example, part 3. The graph of y equals f of x is shown, and we want to sketch the graph of y equals negative f of x. Well, if we learned from last time, this is just going to be a reflection across the y-axis, or not the y-axis, the x-axis. So anytime I have a point of x, it's going to stay the same, but the y values are going to be reflected downwards or upwards, depending on where they were falling initially. So it's going to look something like this, and this would be y equals negative f of x. And in black here, I have y equals f of x. Okay, so if we replace y with negative y, then y equals f of x becomes negative y equals f of x, which is equivalent to y equals negative f of x. And so this replacement, and so if we think about everything we did with each one of these 3 graphs, our x values always stayed the same, right? Like if we look at everything, our x values always stayed the same. What changed was our y values, and the change made to the y values was a reflection. And so they were essentially reversed, right? So if we had a y value at 2 initially, if we did a reflection on that y value, from 2 it would become negative 2. And so that's what we're going to be doing with this lesson, is just reflecting either across the y-axis or the x-axis. All right, so let's look at what happens then if we change the circumstances a little bit. And this time what we're going to be doing is we're going to be comparing the graphs of y equals f of x and y equals f of negative x. All right, so instead of having negative f of x, we have f of negative x. So let's look at this first question. The graph of y equals f of x is equal to x squared, just like is equal to x squared minus 10x plus 25, just like we looked at last time. We want to write the equation which represents y is equal to f of negative x. So what this means is anytime we have a value of x in our function, we're going to substitute it with negative x. Okay, so the x is going to become a negative x, just like this. And so in my original function of x squared minus 10x, we're going to replace that with negative x squared minus 10 times negative x plus 25. And if we were to expand that, we were going to end up with x squared plus 10x plus 25. So what it wants us to do is use a graphing calculator to sketch y equals f of negative x. And then it wants to show us on the grid. So if I input this function, x squared plus 10x plus 25, what we see happening now is a reflection across the y-axis. Right, so if my original function was over here, and that was x squared minus 10x plus 25, it's going to end up being graphed on this point. And so if you notice, these are an exact mirror image of each other. And so my lowest point is going to be down here, and then I'm going to move up like here, up here, and up here. And it's going to look something like this. Alright, so this would be y is equal to f of negative x, whereas this is y is equal to f of x. Now, state the coordinates of the invariant points. Now, you can't really see where the invariant point is in this case. And the reason is because both of these lines are going to be continuing up to the top. And so what we're looking for is where these lines would actually intersect the first time. And so in order to see that, we'll probably have to zoom out. And it looks like the first point of intersection is going to occur right here. Okay? And actually, that would be their only point of intersection. And so if we were to trace that, look for the point where they intersect, and it actually went right to it in this case. So my intersection, let me do that again, intersect, it's going to be at y is equal to 25. And so that also happens to be my invariant point when x is 0, y is 25. And actually all we really need to do is look for when x is equal to 0. Remember last time what we were looking for was when y was equal to 0. That was where our invariant point would be, because that's the reflection across the y-axis, or the x-axis. So in this case, reflection across the y-axis is going to be when x is equal to 0. And in that case, y is going to be equal to 25 here. And so the coordinates of the invariant point is going to be at 0 and 25. Now remember, if it's asking for the coordinates, you need to express it as the coordinates like this. Okay, so part 2, the graph of f of x is equal to x cubed minus 8 is shown here. We want to write the equation which represents y equals f of negative x. So exact same function we were working with before, but now the circumstances have changed and we are doing this instead of what we did on the previous page. So wherever you have an x value, you're going to substitute with negative x. So y is going to equal to negative x cubed minus 8. And we're going to get y is equal to negative x cubed minus 8. Because a negative times negative is a positive times another negative is going to be negative x. Alright, so let's look at what is going to be going on here. We know that there's, well, maybe you don't know this yet, but remember, at this point what we're looking for is a reflection across the y-axis. So I know that my reflection needs to be over here. And so it's going to look exactly like this, but they want us to graph it, so let's graph it. So I'm going to graph my original function of x cubed minus 8, and my new function is going to be negative x cubed minus 8. And so my original function is going to be graphed like this, and my new function is going to come down this side. Alright, and so I'm going to try to draw this as well as I can without plotting all the points. Not bad. Okay. State the coordinates of the invariant points. Well, remember we're looking for when x is equal to 0. So I know that x will be 0, but where does x equal 0 here? Well, that's going to be at negative 8. And how does the graph compare? Well, it is a reflection across this reflection in the y-axis this time. Alright, finally let's look at part 3. The graph of y equals f of x is shown, and we want to sketch the graph of y equals f of negative x. So remember, this is a reflection across the y-axis. And so if this was my mirror image is going to be somewhere around here, and it's going to look like so. Excuse me. So this is y is equal to f of negative x. and this is y is equal to f of x. So there you have your reflections across the x-axis and reflections across the y-axis. And so remember, if we replace, just like last time, if we replaced y with negative y, then f of x became negative f of x. But now if we replace x with negative x, then y of f of x becomes y of f of negative x. So that replacement we were doing was x is, if we're mapping this as x, is going to become negative x. Okay, now comes the fun part, working with inverse functions now. So let's look at the graph of y equals f of x, and that function is x minus 5 squared. We want to write the equation which represents x is equal to f of y, and we want to solve for y. So if we want to switch this function around, y, and the function we're working with is y equals x minus 5 squared. I want to make this x is equal to f of y, right? And so if I'm doing that, then instead of having y equals x minus 5 squared, this is going to become x is equal to y minus 5 squared. Now, to get rid of this squared, remember I got to take the square root of x, and this could be plus or minus the square root of x, and I'll get rid of the squared here because I square rooted it. And now, if I want to solve for y, I'm just going to bring my 5 to the other side, and so this is going to become y is equal to 5 plus or minus the square root of x. So we want to use a graphing calculator now to show what this is going to look like. So my first function was x minus 5 squared, and my other function is going to be plus 5 plus the square root of x, and also 5 minus the square root of, made a mistake here, x and x. Okay, so we'll have our normal parabola graph, and we have our inverted parabola graph as well. And I'm just going to zoom in here so it looks a bit better. And there it is. So I have my new graph, which was formed, and it flipped up here. 1, 2, 3, 4, and 9. So this is my inverse function. So now let's see what's going on here. There are 4 points of intersection for the graph. Right? So I have a point here, and I'm going to use a different color so it's easier to see. So there's 4 points of intersection on the graph. There's 1, 2, 3, and 4. So although there are 4 points of intersection of the graph, so these where my graphs cross, explain why there are only 2 invariant points and mark the invariant points on the grid. So what I'm going to do first is I'm just going to label what my invariant points are. My invariant points are going to be at A and at B. But then I also have these 2 points at C and D. So if I have my points A and B, which are my invariant points, so A and B, first of all, are the invariant points. And the reason A and B are the invariant points is because under this transformation, the A maps to A and the B will map to B, but C is actually going to map to D and D will map to C. So although the points intersect at C and D, these points are not actually invariant. Right? So although, because these intersect here, it doesn't mean they're actually invariant points. And the reason being is because when I perform this function, this transformation on my equation of the inverse function, what is happening is my mirror image is going across, or remember the equation of your mirror image for an inverse function is going to be at x, or at y equals x, right? So this is where your line is going. And so the only two images that are actually mirror images of each other and aren't changing are the A and B. So what happened was this parabola kind of like flipped sideways like that. Okay? And so A and B didn't change, but C and D did actually change. Those weren't invariant points of each other. And so, like, another way to say this is with the invariant points, those same coordinates have to map to the exact same coordinate. So this A had to say A and B had to say B. They didn't actually move. But C was initially in the place of D, and D was initially in the place of C for my new functions and old functions. Because A mapped to A and B mapped to B, but C maps to D and D maps to C. Alright, so we'll go on and it'll solidify your understanding if we do a couple more examples here. Alright, so the graph of all of these graphs are always the same that we're working with here. But the graph of y equals f of x is equal to x cubed minus 8 is shown. Write an equation which represents y is equal to f of inverse of x. Okay, so I have my original function, which is x cubed minus 8, and I want to show y is equal to f of inverse of x, which means that x is going to be y cubed minus 8. And what I'm going to do is I want to try to get this y by itself, and so I'm going to go x plus 8 is equal to y cubed, and then what I'm going to do is take the cube root of both sides, and when I do that I'm going to get y is equal to the cube root of x plus 8. Now what we want to do is graph this function, and if I graph this, x plus 8, I'm going to get something that is going to go across my axis at y equals x. So remember, my mirror image here is going, I should have brought a ruler, but it's okay. So this is my mirror image, and remember your invariant points, and maybe that's a better way to kind of put it instead of maybe making it confusing like this, but your invariant points are going to occur at the axis of reflection. Okay, so since this reflection is occurring at y equals x, that's also where our invariant point is going to be. And so in this case, we don't want to actually mark the invariant point with a coordinate. It just wants us to show where the invariant point actually is. And so it looks like the invariant point is right here, and it wants us to mark the invariant point on the grid, and so I'm just going to call that x. And I guess I should have showed you what that graph looks like, but it looks like this, and so let's see here. If it's -8, it's going to be at -8 again. It's going to be something like that, and then my graph is going to go like that. Okay, so it's the same graph, but it's been inverted, flipped. Now, how does the graph compare with the graph of y equals f of x? Well, it's a reflection in the line of y equals x. And let's go back up here, and we'll look at that again too. So remember, the point of reflection for an inverse function is going to be at y equals x. Right? That's where this line is actually running. This y equals x, and so A and B stayed at y equals x. They run through y equals x, which are the invariant points. But C and D actually they didn't, even though they're intersecting the line, the old or the new line. they're not invariant points because they're not along my axis of symmetry. So next thing we want to do is graph y equals f of x and then sketch the graph of x equals f of y. And so remember that our axis is running along here and along here, and that's not my new graph, by the way. I'm going to graph my new one in blue, or my inverse function in blue. But if I have a point, it's going to go across onto this side. So that's where that new point will be. This new point, if I want to graph this one, it's just going to go on the other side, so straight across. If I'm graphing this, it's going to regraph that one. And my new graph is going to look something like this. Alright, so that's if we compare the graphs as y equals f of x and y equals f of inverse of x. So if we replace x with y and then y with x, then y equals f of x becomes x equals f of y. And so what we're doing, what we're replacing here is x's and y's with x's. Just like we did with inverse functions a couple units ago, or a couple chapters ago. Okay, so let's talk about what reflections are. A reflection, let me move up. A reflection is a transformation which reflects or flips a figure over a line or over an axis of symmetry. Fill in the blanks which summarize the previous investigations. Alright, so let's think about what we just did. If the graph of y equals f of x is reflected, and we're looking for a reflection in the x-axis. If the graph of y equals f of x is reflected in the x-axis, in this case, then it is the graph of y is equal to negative f of x. Okay, so this solid dark line is y equals negative f of x. So every point was reflected across my x-axis here. Alright, so this is a reflection in the x-axis, is if it goes past my x-axis. A reflection in the y-axis, if the graph of y equals f of x is reflected in the y-axis, then it is the graph of y equals f of negative x. And so in this case, it's being reflected across my y-axis. And this is f of negative x. Now, if it's a reflection in the line of y equals negative x, remember this is an inverse function, if the graph of y equals f of x is reflected in the line of y equals x, then it is the graph of x is equal to f of y, or y is equal to the f of inverse of x. And this is a reflection here across y equals x, or y equals f of inverse of x, or f of y. Alright, so only a couple more pages, then I think I'll do another video. It's kind of split this lesson in half. But what we're going to do is look at the graph of y equals f of x and then sketch the new graph, given the reflection that we're kind of ordered to do here. So if I have y equals negative f of x, and I want to graph all these different coordinates here, so that's the function I'm given. Now remember, what does it mean if I have negative f of x? Well, remember that's going to be a reflection across the x-axis. So all my points are going to go across the x-axis. I have invariant points here and here, which are going to stay the same. But all these points, so at negative 4 and 6 is going to become negative 4 and negative 6. Negative 2 and 6 is going to be negative 2 and negative 6. 0 and 4 is going to become 0 and negative 4. 7 and 3 is going to become negative 7 and negative 3 is going to become 7 and positive 3. And I have another invariant point here. So, that did not graph properly. Ignore that, please. So we are going like this. Bam, 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 bam. So that's what that will look like. Okay, so you can probably fill in the rest of these. With this next one, this is going to be a reflection across the y-axis. And so this first one was a reflection across the x-axis. This will be a reflection across the y-axis. And this last one, x is at f of y, is going to be a reflection across of x equals y equals x. So that's going to be where you're going to reflect those points across. And then the last question here is write an equation for each graph drawn in the thick line. So we want to see where these were reflected across. Now this one was reflected across here at y equals x. So the graph of my new line must be, or my thick line here, must be y is equal to f of inverse of x. My reflection here is across the y-axis, and so this equation is going to be y is equal to f of negative x. And then finally my last function was reflected across, oh, it's the same thing. Oh, you know what, it is the same thing. But I think what they wanted to do was, oh, maybe it's not. So this one is going to be y is equal to negative f of x. Okay, so I will have another video for part 2.